Hello guys, and welcome back to another video. Today we are starting a new playlist or a new series for Computational Science 1. It's a second semester course for computer science students at Ontario Tech University, and it's also for some math students as well. Today we're going over error and tolerance. Some of the things I'll be going over today you already know, some of the things maybe not. But I'll try to cover as much as I can from the bases up. So the first thing I'm going to start with is we're going to start easy, which is error. Now I'm going to try to use mostly visuals. We're not really doing much code for this tutorial. For the next one we should be. So error, usually you'll have, let's choose a different color. You'll have some function, right? And this function, you want to find, your ultimate goal is to find the root here. Now, usually here, let me give you a quick example. Usually, if you have a function, if you have a function that is a linear function, so x plus 5. So this is just a line, right, on a plot. Now, if I tell you where is the root, which is where does it meet, right here, right? Well, not right there, technically, it's right there. Where does it cross where y equals 0? You'll say, okay, if I set my function to equal 0, which is aka y equals 0, and then I solve for my x, I will tell you where it crosses 0. So there you go. So we know for this function, we have a root at x negative 5. Now, you can also do this for low-degree polynomial functions, like a parabola, for example. X squared, and this one obviously we know if you sub in 0 here, well, not 0, if you make the function 0, you'll get x squared, and we know this function meets at x equals 0 as well. You could do it for other low degree polynomial functions, this is finding the root algebraically, which is easy for some functions but not all functions. For example, if I give you cos x minus x, like, do you even know where to start, right? Okay, like sure, you want to start this at 0, there you go. What now? So for stuff like this, that's why we use computers, and we compute the root. We compute an approximate root. Sometimes we get the exact, but sometimes we don't, and it takes too much energy and too much computation and time to get the exact root. So we're like, you know what, we'll accept some level of error, and that's what error is. So let's say we compute it here, and we're like, this is the closest we can. The current algorithm we're using, if we keep going, this is just going to take forever. We're not going to get anywhere. So we're like, okay, what's the error here? Well, this is obviously your error. And by definition, your error is the deviation from a computed value. So obviously this is our computed value. What is the error is how much we deviate from the real thing. All right, now in your head, you're like, if I have a computed value, I have an error, can't I just add them together to get the actual root? Now, the error is not necessarily the distance between your computed and the actual value. You can use different means to explain an error. But you could even use the height. You could say, this is my error now. So there's different things you could use as your error. I'm just, for easy sakes or easy to explain, I'm using this as an error. But usually that's not the case. Because obviously if you do, you can just compute the real root and you would not even have an error. But that's like the definition of error. Now the second thing we're going over is tolerance. And by definition, tolerance is the level of error that is accepted. So remember, here we found an error. So if I say, well, this is my tolerance, then this computed value don't mean shit, basically. Like, I can't use this. This is too much error. It doesn't mean anything. Now, if I find another error, if I find another computed value here with some, obviously, it still has some level of error, right? But since this second computed value, the error here is lower than my tolerance, I'm like, you know what? Since it takes too much computation and time to find the root, this is acceptable. So I will now take this xr, this x subscript r, plus minus some error, and I'll use this as a root. This is an approximate to the root. It's just good enough. And so that's if it's lower than the tolerance. That's what the tolerance is. Now is the last thing, which is convergence. Convergence is basically when, here I'll actually do the definition. Convergence is when a solution was found with an error smaller than the tolerance. So if my error is smaller than my tolerance, then it converges. So this example, this does not converge, this converges. And that's what convergence is. Now we're going to go over the more important things, now that you know definitions, which is computing error. How can you find an error for some computed value xr, right? So xr is a computed, here, xr is a computed value. The question is, how do we find the error for this computed value? Remember, here we have some value. How do I find this error? Right now, we're going to go over two methods. So I have method 1. What is method 1? Now, you could think about, well, the error by definition is the deviation from a computed value. And theoretically or conceptually, the closer you get to a root, the smaller the error becomes. Because if you get the actual root, you have no error. And the more you get further from the root, the bigger your error becomes. It only makes sense. As you can see here, the further we get from the root, let's use a different color. The further we get from the root, the bigger our error becomes. And so if we know that, then, well, can't we use oops, I had like a brain lag. Then can't we use f at the computed value as our error? Now, why does this work? Because, well, for this example, as we could see, here, actually, I'll draw a new example. For this example, as you could see, if we, there you go. Let's say this is our function. Actually, let me make a more steeper decline like this. I don't like this. Hold on, guys. Let me make this clearer and prettier. So there you go. And we're gonna slowly, okay, I'm gonna zoom out. We're gonna slowly descend. There you go. So now, if I have one value here, xr, and I have another value here, xr. These are just two random computed values by an algorithm. You run it the first time, it gives you this. You run it the second time, it gives you that. Okay? So actually, for this one, I'm going to put it on top instead. Okay? So now what we said is, okay, my error, the way I'm going to compute error for this function, I mean, it's the absolute of whatever my computed value is. So the function at the computed value for this here is this one. All right, so this is my f at xr, right? And then here, this is also my f at xr. All right, except this one will give me a negative value. So keep that in mind. All right, now we know as this approaches the root, this gets smaller, right? As you can see, if I recompute this and I get another value here, so let's say this is x1, this is x2. This one here is clearly smaller than the one before it. And we know error, as you get closer to a root, it gets smaller. So, oh, this works as an error. Conceptually, this is the same thing. And so, obviously, same thing on this side. We'll have, let's say, x2. And here you'll have x1. This is obviously smaller. So my error can easily be, like we explained it up here, whatever the function is, and we put the absolute, because if it gives me negative, I don't care if the error is negative. I don't care which direction the error is in. I care how much it is, like its value. That's why we put the absolute. So that is one way we can calculate the error. Now, what is the disadvantage of this method? And that's what we're going to go over. Because that's why I tell you guys there's multiple ways to calculate error, because there's disadvantages to each way you choose to calculate your error, depending on the function. That's so much talking. So now we're going to go over the disadvantage. Now, obviously, we know our error equals the absolute f of x. There you go. And then I'm going to choose my tolerance level to be 1. Okay? So now, my function that I'm going to choose for this to demonstrate the problem with this is going to be x squared plus half. Okay? So now, let's say we run our algorithm, and I tell my algorithm, can you please find the root here? So let's do that. So my algorithm first will do, okay, let's do x. So x1 is going to be, let's say, at 2, which, should I do 2? Actually, no. Instead of doing multiple, I'll just do the first one. So let's say that the first guess the algorithm goes to is x at 0. So I'll do f of x. Obviously, we'll sub in 0. And this will give me 0 squared plus a half, which equals a half. Okay? So now my algorithm, what it says is, okay, my first computation at x0 equals 0, which equals a half. The function equals a half. Yeah, I shall write it right under. The function equals a half. Well, what's my error? My error is the absolute at f of x, which equals the absolute of f at 0, which equals, again, the absolute of a half, which equals just a half. So we know here my error equals a half. And again, my tolerance, I defined it earlier to be 1. And so what the algorithm is going to say, since E is lower than the tolerance, this converges at x equals 0. So you see now my algorithm, what it says is this function has a root at x equals 0 plus a half. That's my error, right? Right here. And so now you might think, oh, okay, this function has a root, guys, at a half, well, at 0 plus a half for the error, plus minus. And then, but if you go on Desmos and you take this function and we do a plot, here, actually, I'll do a double-sided plot. There you go. So we know x squared actually looks like this, right? X squared looks like this, we spoke about earlier, and it has a root at 0, but this is x squared plus a half. So this looks like this. It shifts up a half, and, well, then there's no root. But our algorithm just said there is a root because the error is lower than tolerance. And so that is the first issue with method number 1. Okay. Now we're going to go over method 2. Okay. What method 2 is, it says error equals x at I plus 1 minus x at I. Now we'll go over what i's and x at I mean. But I like to explain through examples. So usually your function, so we're going to draw a function here, and let's say my function goes like this. Okay, your algorithm, usually the first time it runs, it will go, okay, x is 0, that's my first x, and then it'll run one more time. It iterates, right? It's like a for loop. If you're a computer science student or even a math, you should know what a for loop is, or a while loop. So it's iterative, so it keeps running, and the first time it runs, x at 0. Second time it runs, x at 1. Third time, x at 2. And then x at 3, x at 4. Oops. And then x at 5. And if you see a pattern here, the more it iterates, the smaller this distance becomes. So see, this distance is smaller than this distance. And conceptually, we spoke about earlier, the definition of error, or the concept of an error, the closer you get to a root, the smaller the error becomes. And as you can see, the closer we get to a root, the smaller this distance becomes. So conceptually, we can use this method. The difference between two guesses can be an error. Because the closer we get to the root, that gets smaller. And so, okay, what's the disadvantage with this method? Oops, what happened? There you go. So here, we know now our new error, this new method, x at I plus 1 minus x at I, right? We'll set our tolerance to be 0.5, and I'll choose for my function to be 1 over x. Now, the couple things about this function that I want you to know. Well, one, how does this function even look? So this function looks like this. Okay? 1, you can't have x at 0. That is because, well, 1 over 0 is undefined. So that's not possible. And the second thing is, what can you sub in? What can you sub in here to make this equal 0? Nothing. And so that's why you'll never have a root for this function. All right. So now that you know this function has a root, now obviously for this example, just by looking at it, you know. But for some functions like cos x minus x, you don't know that. And so that's why this algorithm will break under certain conditions. Now, obviously for this one, we know there's no root, but for others, we don't. So let's assume we don't know this has no root. And let's keep going with our algorithm that finds a root. So let's say the first guess says, okay, my guess at 1 equals 2. So my function at 2 equals 1 over 2. And then I'm like, okay, my second guess is going to be 3. So my function at 3 equals 1 over 3. And then x at 3 equals, let's say, 4. And this will obviously keep going until you have something to break the loop. So here we'll do this as the last one. Right? And this will keep going until you stop it eventually. But let's say it stops here. Okay? Your algorithm stops here. I'm like, okay, I want to now calculate the error. So I have two values. I have the function at 4 equals 1/4. And I have the function at 5 equals 1/5. Okay? So what is my error? And I'm like, okay, so my error is the absolute value of x at I plus 1 minus x at I, right? So obviously we know here it's 3 and 4. So this will be, this will be x at 4 minus x at 3. Remember, if this is 3, this is 3 plus 1, which is 4. All right? And so what are my values here? Well, what do I have? I have 1/4 minus 1/5. So 1/4 minus 1/5. And this is basically 1/4 is what? 2.5 minus 0.2? Right? Pretty sure that's what it is. And so what we'll get is just 0.05 absolute. Well, we don't need the absolute here. They just drop because it's a positive value anyway. So now that we have this, that's my error. And so my algorithm will say is, okay, does this converge? How do I know it converges? If the error is lower than the tolerance. What's my tolerance? Is 0.5. So my error 0.05 is lower than 0.5. So my error is lower than my tolerance. This converges, right? But we know, obviously, this doesn't converge. This doesn't have a root to begin with. And so, you see, this method also has an issue that you have to know the function beforehand, and you have to be careful with the tolerance you're choosing. And that is the same for both methods. Now, in conclusion, you could say, well, how about this? If the distances change, I know my algorithm is making progress. Right? If your distance doesn't change, you know each guess you're making, well, if it's not getting smaller, if it's staying the same or it's getting bigger, you're not making any progress. You can say, okay, stop my algorithm. There's no progress. You can also use this to calculate when to stop, and you can combine it with method 2 to be like, am I even getting close to a root? Is this even getting smaller? If it's not, then it doesn't matter, right? So these are, like, you can combine these two to have now a third method to calculate error. And so that is about it for today's video. That's all I wanted to cover. Is I wanted to cover errors, tolerance, convergence, how there is different ways to calculate errors, how there's disadvantages, and there's obviously more ways to calculate error than this. In the next video, we're going to be going over convergence. And then we'll also, I believe, we'll go over how to calculate errors for bisection. So yeah, I'll see you guys in the next video where we'll talk about bisection, which is, it's an algorithm for finding the root.